Okay, this video is going to be the last in a series of videos where we're looking at the how to evaluate complex contour integrals manually without using any theorems. So in the last three videos, we looked at this integral and we evaluated it along different contours. So we were evaluating this from -1 plus I to 3 plus 9I. So in the first instance, we worked this out along a path which was in the form of a polygon made out of a horizontal line component and then a vertical line component. So let's call this C1. And then in part 2, we saw how to evaluate this if the path joining the 2 points is a straight line, which is making an angle. In this case, the angle was 2. And then in the last video, which was part 3, we looked at how to evaluate this along a parabola, where the parabola was defined using parametric equations. So our contour was the section of the parabola from here to that point. Okay, now so that is covering the different possibilities. In this video, we're going to look at how to evaluate a contour integral if the path has got circular symmetry. That means the path is either a circle or part of a circle. So here is an example. We're going to be looking at how to evaluate this integral from 2i to -2i along the circle mod z equals to 2 traversed in the clockwise direction. So let's just do a sketch of what is happening here. So we have got a circle, mod z equals to 2 is a circle of radius 2. So there is our circle there. And then in this particular question, our contour is from 2i, so 2i there, to -2. So this is going to be our contour, and the direction is the counterclockwise direction. So the way to do this is to introduce parametric equations. In particular, we're going to express this in polar form using polar coordinates. So from mod z equals to 2, if we write this in terms of x and y, this is square root of x squared plus y squared is equal to 2. If we square both sides, this is x squared plus y squared equals to 4, which is just your standard equation of a circle centered at the origin with radius 2. Now, so what we're going to do is we are going to let x be 2 times cosine theta. This is just your standard polar coordinates, where 2 is our r in this case. Then y is going to be 2 times sine theta. So in our integral, we have got dz, we have got mod z. So we need to write those in terms of theta. So z is equal to x plus iy. If we plug in these two, is going to be 2 into cosine theta plus I sine theta. Then mod z is x minus iy. So that one is going to be cosine theta minus I sine theta. Now, so this is well and good. However, this is where Euler's equation come, to be extremely useful. So here, for instance, we need to find the derivative of mod z, because actually we need to find the derivative of z. So we could do that by differentiating this, in which case we have got to differentiate two functions. But if we express this using Euler's formula, this becomes 2e to the I theta. Then if we were to differentiate it, instead of differentiating two functions, we just have to differentiate one function. It's the same thing if we were to differentiate this one. This one, by the way, becomes 2e to the minus I theta. So that's what happens when you take the complex conjugate. So from here, it means dz is going to be equal to, so the variable here is just theta. So if we differentiate that thing with respect to theta, we're going to have to multiply by I, which is the derivative of the exponent. Then this to the power of 4, which is going to be this thing to the power of 4. 2 to the power of 4 is 2 to the power of 4 is 16. I just noticed that there is a going to modify that. So there's a 3 multiplying the z to the power 4. It's going to be 16e to the power of negative 4I theta. Then so our integral is now going to be, so if we call it I, by the way, before we go to that, let's just generalize in terms of transforming from an equation in terms of mod z to its parametric form. So in general, if we have got mod z equal to r, then this in parametric form is going to give us z equals to re to the I theta all the time. In our case, r was 2. In fact, even if you have got mod of z minus z naught equals to r, then z minus z naught is always going to be re to the I theta, using the same process that we just demonstrated. All right, now, so back to our integral. So our integral I is going to be integral of 1 plus 3 times mod z to the power 4 is 16e to the minus 4I theta. And then dz is 2i e to the I theta. So 2i e to the I theta d theta. And then 2i is a constant. Oh, before we go to that, the limits are now going to be in terms of theta because it's just an integral of theta. Now, at 2i, theta is pi on 2. And then at negative 2, theta is pi. So we're going to be integrating from pi on 2 to pi. Lower limit is pi on 2. Upper limit is going to be pi. Right, so then what remains is just the process of integrating pi on 2 to pi. If I multiply through, so I've already factored out the 2i, multiply through by this, we're going to have e to the I theta times 1, and then this is going to be 48e. This times this is going to be minus 3 I theta d theta. And then we just integrate as usual. So this is going to be 2i, going to be e to the I theta over I. We're now integrating. This is going to be 48 over negative 3i, e to the minus 3i theta, pi on 2 to pi. The i's are going to cancel out on account of this factor of I outside. So we're just going to have 2 times e to the I theta. This is going to be minus 16e to the minus 3i theta, pi on 2 to pi. If we plug in pi, this thing is going to give us e to the I pi minus 16e to the minus 3i pi. Take away, when I'll plug in pi on 2, e to the I pi on 2, minus 16e to the minus 3i pi on 2. Okay. And then we just evaluate this. E to the I pi, this one is just negative 1. So negative 1 there. E to the minus 3i pi is also negative 1. So e to the I times odd multiples of pi is always going to be negative 1. So it's going to be minus 16 times negative 1. Then e to the I pi on 2 is I, that's this one. And then e to the minus I pi on 2 is negative I. So from this one, we're going to have 16 minus 1, which is 15. And from this one, again, we're going to have 16 minus 1, but there's going to be 15i this time. So this thing is going to give us, sorry, there's going to be, wait. So what's happening is this is positive. Just one moment. Okay, sorry, there is a small just a mistake. This should be negative 3i pi, and then e to the negative 3i pi is positive I. So it's going to be negative 16i minus 16i, which is going to be negative 15i. So this is going to be 30 into 1 plus I. And so that is going to be our final answer. All right, at this point, we are going to give you an opportunity to evaluate something similar. We're just going to give you a chance to work through this, evaluate this from 1 plus I to minus 1 minus I. This is 1 plus 1 over z dz bar along the circle mod z equals to root 2 this time in the clockwise direction. In the clockwise direction. All right, so if you just want to have a go at this, you can pause the video, and then when you continue the video, then you can compare with our solution. All right, we're now going to scroll down to our solution. for this question here. We wish to thank you for visiting our channel and watching this video. We hope that our videos are useful. We do implore you to subscribe to our channel to support it. All right, so in this case, we're integrating from 1 plus I to negative 1 minus I. So along the circle mod z equals to square root 2. So we parameterize in a manner that we've already demonstrated before. So in this case, we're going to get z is square root 2I theta, square root 2e to the I theta. Then mod z we just get from here by negating the exponent. In the integral, we've got d mod z. So we differentiate this one. That's what we get. Just going to multiply by negative I there. So if we plug this thing here, at 1 plus I, theta is pi on 4. So it's going to be our lower summation limit. And then we go in the clockwise sense this time. So that means this angle here is going to be negative 3 pi on 4. If we're going in the clockwise sense, this angle would be 5 pi on 4. So just be careful to be clear which direction the question is asking. So in this sense, it would be from pi on 4 to 5 pi on 4, but it is in the clockwise sense, so it's to negative 3 pi on 4. Right, so this is 1 over z here, and this is a dz bar here. If we remove the brackets, okay, the negative I we're going to factor out. Then this term is just going to sit here. It's times 1. Then this term times this term, the square root 2 cancels out the e's. If we bring them to the numerator, got e to the minus 2I theta. And then after that, it's just an integral of theta with respect to theta. So here we're going to divide by negative I, here divide by negative 2I. There is negative I sitting outside, so if we combine those, then the negatives go away and the i's cancel out. So we just have this thing here. We plug in negative 3 pi on 4. That's what we're going to have. And then this is what we have if we plug in pi on 4. This one we're going to resort to Euler's formula. So we're just going to use e to the I theta cosine theta plus I sine theta. Here theta is 3 pi on 4, which is in the second quadrant is actually 135 degrees. So cosine of that is going to be negative, and sine of that is going to be positive. E to the I pi over 2, e to the 3I pi over 2, it's just going to be negative I. And we do the same thing here. Negative pi on 4 is in the fourth quadrant, so cosine positive sine is negative. And this one, again, e to the negative I pi on 2 is negative I. And you're going to notice that these two are going to actually cancel out. And then simplifying these two, there's going to be minus 1 here, and minus 1 there is going to be minus 2, and then it's going to be 2i there. So this is going to be our final answer. All right, thank you.